All, welcome to the 64-bit edition of the SecurityTube Linux Assembly Expert course and certification. Now in this video, we will finally write our Hello World assembly language program. So you should already have NASM, LD and all of that installed if you followed the previous videos. And before we begin, I'd just like to mention that when you write an assembly language program, you have an option to either use the AT&T syntax or the Intel syntax. Now, without going into too many details about similarities or differences, all I can say is, regardless of whichever one you use, you should be able to accomplish the same task. In the sense, it's more about what you prefer rather than any hard and fast reason to use one. I will be using the Intel syntax for this entire course, just as I have done for the 32-bit course. Okay, so let's go ahead and begin writing our Hello World program. And as you can imagine, the very first thing, of course, is to go ahead and create a file. So I'm going to be using the Vim editor because I'm more familiar with Vim and all of that. You can continue to use Pico or Nano or Vim regardless. Choose something which you're familiar with and that should do. Right, so let me type in hello world.nasm. Okay, now let's go back to the slides. So we first need to define the text section. Now what is the text section? Well, it's that place of your program where all executable code needs to be put. So let me go in here and type in section.text. So the section keyword tells the assembler, it's an assembler directive, that we are defining the text section. Now we need to define the data section so that we can put the string hello world in it. So let's go in here, section.data, and now let's define our hello world string, hello_world. This is the label name, and then we'll define a series of bytes using db or define byte, and we'll type in hello world to the SLAE 64 course. Now let's go back to the slides. Now you have this huge text section, but how do you go ahead and tell the assembler and linker where you would like the entry point into your program? So to do that, we need to do two things. The first is define a label which will point basically to the beginning of our entry point. Let me call it _start, and then to use the directive global and basically tell that _start is where we are going to start the program. Now we need to write code to print to screen and then finally to exit gracefully. So I'm just going to put in two placeholders for the time being, print on screen, exit gracefully. Right, now let me go ahead and fill both of these in. Now one of the things which you're probably thinking is, if you had to write a print on screen source code, imagine the number of hoops you would have to go through, right? You would have to figure out how to communicate with the external device, which could be a CRT monitor or an LCD or something else. Then you would have to figure out how to position the string, and then finally how to write it. There's a ton of complications in there, where really you do not want to reinvent the wheel for every single program which you write. And this is where you would want to leverage the operating system to help you with tasks such as writing to disk, printing on screen, etc. Now the way you leverage the OS is by using what is called system calls. Now system calls are a very simple interface by which user space programs or code can actually call kernel space functions. These would include writing to disk, reading from files, and a ton of other possibilities. So where are these system calls defined? Now on an Ubuntu machine, this is defined in user include x86_64 -linux -gnu /asm unisted_64.h. Now if you go inside the file, you would see that you have the read syscall in here with the value 0, you have write in here with the value 1, and so on and so forth, right? Many of them. Scroll down to see the whole list. Now how do we invoke system calls, right? We invoke them by going ahead and using the syscall keyword. Now how system calls work, what goes behind in the background, between user space and kernel space code and all of that, VDSOs, and other stuff is beyond the scope of this series. And if you're interested, it's really more in the realm of operating systems and system programming and all of that. You could go ahead and look into this blog link. Scroll down at the end of the blog post. You should find more links which you can reference in case you're more inquisitive or curious. Now, we have two tasks in hand. The first is to go ahead and write the hello world string on the screen, and the second is to exit the program gracefully, right? So how do we use the syscall interface? Now how do I tell the operating system that I would want you to take this string, write it on screen? So the way you would do that is by using registers and loading them with the appropriate arguments based on a well understood convention by both you and the operating system, right? So really, here is the simple way by which you can invoke a syscall. The system call number needs to be in the RAX register, the first argument in RDI, second in RSI, third if present in RDX, fourth in R10, fifth in R8, and sixth in R9. Now again, you could of course have much lesser arguments, in which case most of these may not even be applicable, right? So in our case, one of the other things you need to also keep in mind, though we aren't going to use it, is the return value of the syscall is in the RAX register. Now with this background in place, let's see how we can call the write syscall. Now I said the first thing you need is the system call number for write. So if we go back in here, you would find that write has the syscall number 1. Fantastic. Let me go back in here and let me start cranking some code. So I'm going to say move the value, which is, I'll come to what move does in more detail later, but in very simple terms, it just moves data from one location to the other, which could be registers, memory location, etc. So move the value 1 into the RAX register, right? 1 is nothing but the syscall number for write. Now the first argument, and you can do a man to write to see the man page, is really the file descriptor to write to. Now in our case, we want to write to the screen, which is std out. Std out has a value of 1, and hence we need to load RDI with run based on the convention we just saw. So RDI has 1 as well. Then we need to put in the address of the string which you want to write on the screen, and that address needs to go into RSI. So I'm going to say move RSI, and I can get the address by just using the label name directly in here. So move RSI comma hello underscore world will actually take the address where the string is located and referenced by the label hello underscore world and put it here. Finally, the length of the string which I would like to write needs to go inside RDX. So move RDX. Now one of the ways is you can go ahead and count the length of the string. There is an easier shortcut though. Let's say length EQU is really equals, and then dollar stands for the current label location minus basically the location for hello underscore world. And if you think about it, it's a little trick to actually count the number of bytes occupied by the hello underscore world string. So I'm going to go in here, I'm going to basically say length. And now that we have all the arguments and the syscall number loaded into the appropriate registers based on the calling convention, I'm going to call syscall so that the system call is invoked to write hello world to the SLE64 course on the screen. Now once this is done, we need to exit the program gracefully, and for that we need to call the exit syscall. So let's quickly go ahead and check where exit is. Here is exit, and the syscall number for exit is 60. So I'm going to say move RAX 60, and then the first argument goes into RDI, and let's remind ourselves the first and only argument is the status you would like to return back to the environment which invoked the program, and let me give the status as 11. Right, typically it's given as 0 if there are no errors, but let's say 11 so we can check it, and then I call syscall to ensure that the system call is invoked. Right, okay, I hope there are no typos. Let me go ahead and use NASM to assemble this program. Fantastic. Now let me use LD to link it. Awesome. And now let me run this program. And fantastic, as expected, we actually see that we have our hello world to the SLE64 course, and of course then the bash prompt comes in Pentester Academy. We can fix that real quick. Let me open the file, and let me actually go ahead and add a 0A at the end. Just so that we can basically have it in a separate line. So I'm assembling and linking it again, and now let me run it. And there we go, right? This is the output the program gives you, hello world to the SLE64 course. So if you're here and this has worked, congratulate yourself. Basically you have written your very first assembly language program, which is the hello world welcome program. And we're going to do a lot more stuff after this, and of course more challenging ones as well. Now here is the exercise I want you to do, and which I will solve for you in the next video, which is take GDB and go ahead and run the program from within GDB and step through it and observe how the CPU registers, memory locations and all of that, either changes or works, so that you have a firm understanding of what really happened here. So to summarize, the key takeaway is really to understand the system call and how to invoke them. And if you're coming from the x86 background, you would actually see that the registers which are used have been changed in the case of 64-bit, right? So that's all in this video. I hope you enjoyed it, and see you in the next one. Bye-bye.